Hello, this is Mr. Collier, and today we're doing kinematics with some differential calculus. Okay, so firstly, we're going to look at some problems here. A particle moves in a horizontal line, so its position from a fixed point after t seconds is s meters, where s equals this function right here. Okay, so find the velocity and acceleration after 1 second. So the velocity is just the first derivative. So that's ds dt. We're always differentiating with respect to time. So that's 10t minus 4t cubed. So that's the first derivative. That equals velocity. Okay, so therefore the velocity at 1 second equals 10 times 1 minus 4 times 1 cubed. And next, the second derivative, or the first derivative of the velocity, is going to be the acceleration. So dv dt equals the derivative of this, which is 10 minus 12t squared. That's the acceleration. So the acceleration after 1 second is 10 minus 12 times 1 squared, which is negative 2. Okay, so that means it's slowing down. Is the particle speeding up or slowing down at t equals 1? Well, I'll just answer that question. Because, actually, let's get the answer for this part. This is 6 meters per second. So if the velocity and acceleration are opposite signs, then it's slowing down. Okay, so the velocity, the particle is moving in the right direction. It's got a positive velocity. It's going 6 meters per second. But the acceleration is negative, so that means the speed is slowing down. So it is slowing down. Okay, next one we have a particle moves in a straight line by this equation, so it's got cosine in here. So sketch the graph against time. So let's see what that graph looks like. Let's try to draw that a bit straighter. So this is cosine 2t. Now if we plug in t equals 0, we get cosine 0, which equals 1, and we get 2 minus 2 is 0. So we have 0. This is going to go between 0 and 4 because the magnitude of the cosine curve is going to be 2, so we're going to go between 0 and 4. So I'm going to make 4 tick marks here. This is 4. The principal axis is going to be right in the middle at 2. I guess I don't need to draw that in there. Yeah, so 1, 2, 3, 4. So I'm going to start off here, and then if I have a time like, if this is going to be pi over 2, then we have cosine equals to 0, right? That happens when we have pi over 4. Okay, so when we have pi over 4, so I'm going to go up in pi over 4s. Pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and then pi. So let's look at what happens at pi seconds. When we have pi seconds, we have 2 pi, so cosine is again equal to 1, so we'll be back down here again, right? And in between there, we'll have a maximum. Okay, and the inflection point is going to be right there. So the cosine curve, oh, that's a horrible drawing. It's going to look like that. Still pretty bad. My scale is not very good either. This would be better if you drew a nice curve on a graph paper. Okay, 1, 2, 3, 4. So at 2 pi, again, you're going to have the minimum occurring again, and in the middle of this, you're going to have maximum. Oops, let's try that a little bit again. Okay, so something like that. So it's going to be like a cosine curve that keeps continuing like this. So it oscillates between 0 and 4. Find the times when the particle is stationary and the displacements at these times. So remember, this is time and this is displacement here. Or actually, we often call that S. Well, we call it X in this case, okay. Alright, so we can use calculus to find the derivative and then set that equal to 0, but you can see clearly from the graph that the stationary points are going to be at these locations. Okay, so when we have, let's do t and x, little table here. When t is 0, we have the displacement is 0. When the time is pi over 2, we have displacement is 4. When it is pi, it's going to be 0 again. Then we have 3 pi over 4. We have 4, not 3 pi over 4, sorry. Pi, we have 0. At this point here, which is 3 pi over 2, we have another maximum, which is 4. So it's basically oscillating. If I want to describe the motion, as oscillating between 0 and 4. Okay, in this next example, we have a function that models the height of a bungee jumper from a bridge. So the height obviously decreases till it gets to a minimum, then increases because the bungee jumper is kind of bouncing up and down, and then comes to a stop eventually. How high is the platform above the ground? So for that, we just plug in time equals 0 into this equation, and we can get that value. This is a several part question where I know I'm going to need my calculator. So I already typed in the function in your calculator. So if you have the function typed into your calculator, you can just go to number and then find out what that value is. So when time equals 0, we have 612 meters. I'm assuming this is meters in seconds. If AJ is left to hang forever, how high will he be above the ground? Well, that would be the what this function is approaching here, this horizontal asymptote, right? Whatever that value is. So as t goes off to infinity, then this value here approaches 0. So the asymptote is actually y equals 202.6. So this should be 202.6 meters. And next question is, at what time is AJ moving the fastest? And I'm going to show the next one. What's his maximum velocity? So those are two different questions. One's talking about speed, and one's actually talking about the velocity. So as this person's descending, they're kind of speeding up, and then going faster and faster. So it's probably right in here is the fastest point. Then they slow down, and they come back up, right? But for the maximum velocity, that means velocity has magnitude, so it's kind of implying the maximum velocity would be when it's positive, so when it's actually increasing or coming back up. Okay, assuming up is positive and down is negative. Anyway, let's look at what we see on the calculator when we do that. So when you go to graph the function, you might want to go to shift plot and set up something that looks like it makes sense. I'm going to go from 0 to 1,000 on the y values. That's 0 meters to 1,000 meters, and 0 to 30 seconds. I should be able to see a lot of it. So when I plot it, it looks like this. So kind of similar to what we see in the graph here. But if you want to see what the velocity looks like, you can go to go back to the function. In the second one, you can click here. Click this button, gives you lots of options. Go over to the fourth one over here is the derivative. And then you can type in f1 of x in the numerator and then x in the denominator. That's always just x. And that will graph the derivative. So if I go back to this and I don't want to see the original function, just the derivative, I can take out that check mark and just go plot. And it looks like that. Now, there's some places where the velocity is negative, so I'm going to change this again. The plot to include negative values. It doesn't look like I need 1,000, so I'm going to do maybe negative 300 to 300, and let's see what that looks like. Okay, so the maximum velocity is actually right here because that's the maximum of this function, but when is he moving the fastest is actually right here. Okay, it's a negative velocity, but speed is the absolute value of velocity. So right there is where AJ is moving the fastest. So, but actually, if you go to try to find the extremum here, it doesn't work for the derivative. So we need a way around that. But the way around that for the HP prime is at these maximums and minimums, the next derivative equals 0, or in other words, the acceleration equals 0. So when I go to apps, I can actually do another one here, and in F3 I can create the acceleration by getting the derivative of F2. So I can go over here, get the derivative, type in F2 of x, and then the denominator just x, and we'll just show that. So there it is, and we need to find the 0. So you can click over here and click on root. That'll find 0. So 3.46 is the time when AJ is moving the fastest, is 3.46. Okay, let me show you how to do that on the TI-84. For those people who have TI-84, it's actually much easier. You can just do math, go down until you get to the derivative here, and you can type in x, and this is you click on variables, go to get y1, and this is x. And when you do this, you will actually be able to get the minimum right here, and it corresponds to 3.46, so it's the same thing. Okay, so 3.46 seconds is when it's moving the fastest, so that's like right about like here somewhere, the same as the point of inflection. Okay, then it's slowing down, then coming back up. So the maximum velocity, let's look at TI-84. The maximum velocity is actually when the velocity is positive, so the positive maximum here. So we can get that maximum value right there. And let's go over here, enter, and go over here. Alright, and then, oops, it's slowing down a bit right now. My guess is going to be over here. Alright. Oh, let's try to go closer to the maximum. There we go. So that gives us, it takes a while, 11.7 seconds, and 49.8 is actually the maximum velocity. So max velocity is 49.8. Okay, that's meters per second. Okay, next question, state the first three intervals. We're just going to do the first interval, where speed is decreasing. So speed is decreasing when the velocity and the acceleration are opposite signs. Okay, when the velocity and acceleration are opposite signs. Let's see if I can do it in the TI-84. Let's go to apps, and let's plot the velocity and the acceleration together. And where are the opposite signs? Well, right here, the green one here is the acceleration, so it is positive, and then velocity is negative all the way up to these points. So if we know the roots here, we get the roots here, then we can answer the question. So we actually do know the root right there is 3.56, I believe we said, right? And now we go over to find this one right here, so just the velocity. So I'm going to just get rid of the acceleration. So we need to find this x-intercept here for the velocity. So we go to root. Oops, let's click on here first and then go to root. Okay, so that is, root is 8.27. Okay, so it's from 3.46 seconds to 8.27. 27 seconds.